Good evening, everyone, and welcome to January NanoTalk about climate and climate change. My name is Maria Solagazzi. I am a student of interdisciplinary natural science at the ETH of Zurich, and tonight, together with Yasmin, we will moderate this evening. Thank you for being here. We are very pleased to welcome you as our event tonight. During this evening, we will have two talks. The first one given by Amy Macfarlane, who will tell us about her unique experience during the international expedition in the Arctic, the MOSAiC expedition. And after, Giulia Mazzotti will talk about the use of drone in the study of climate change. Following these two presentations, we will have also a Q&A when you can also interact with us with Slido, but we will explain that better next. But before we begin, I would like to tell you why we have chosen to talk about this subject tonight. Climate change is, as we all know, an issue of fundamental importance to everyone, not just for science, but for all the society. So in fact, it's a real point of contact between science and society. This is why it's wonderful for us to welcome tonight two young female scientists who will enable us to have a fresh look at this issue. They will share their unique experience with us and give a closer look at the importance of snow in the climate change. Thanks.
Hi, I'm Yasmin, your co-host for tonight, and let me introduce to you REACH, the organization behind the NanoTalks. REACH is a think tank that is engaged in the interaction between scientists, politicians, and the public to create a science-friendly culture. If you want to learn more about REACH or join our community, visit us at reach.ch. An important mission of REACH is the training of young scientists like Maria Sole and I within their SIMPACT program. SIMPACT gives us the opportunity to participate in workshops on scientific storytelling, blog writing, and critical thinking. And it also gives us the opportunity to organize public events like the NanoTalk tonight. Before I introduce to you the first speaker, I would like to remind you or invite you to ask questions. You can ask questions at any time during the talk. Just simply go to slide.do and enter the code nano-jan. So with this said, I'd like to introduce Amy, a PhD student from the Snow and Avalanche Research Center in Davos. Amy had the unique opportunity to join the MOSAiC expedition to the Arctic Sea, where she spent 8 months adrift, investigating the snow on the ice surface. With this, I'm looking forward to your story, Amy, and with this, the stage is all yours.
So I'd just like to say thank you, Yasmin and Maria Sole, for the introduction. I'll just share my screen now. So yes, thank you for the introduction and thank you for having me today. It's really exciting to be able to speak to this to the public about what we do in this field. And I just need to start off by saying I was part of this huge international expedition. So I obviously need to thank everyone involved with gathering data, the logistics. The expedition was hosted by the Alfred Wegener Institute in Germany. They provided the resources for us to be able to do this. So with that, I'll begin my presentation. So I'm going to start off by just saying while 2020 was quite an unusual year for most people, I was actually very close to the North Pole, about 200 kilometers away. Working in an environment like this. So before the team left, which contained about 50 scientists and 50 crew. We actually thought we were going to be the most isolated people in the world this year. And then it turned out that we were probably one of the largest gatherings of people. So it was very strange in that sense. But yes, it just happened at quite an unusual time, I think. So in this presentation, I'll talk about how I got there, what's my background, and then what the expedition was like. This was my first time on an expedition of this size to the Arctic. So I'll say about life on board, the research that we were doing, and then I'll tell you a little bit about my research and what I was specifically looking at. So you'll recognize this from the image of the poster. I quite like this image because it really reminds me of one particularly cold day in April. It was around -40 degrees. It was extremely windy and very humid. So you can imagine it's not a dry cold that you get, for example, in the Alps, but it's very, very cold and also can be quite dangerous. So before we went on this expedition, we had a lot of frostbite training just to be able to handle working at temperatures like this. For example, getting ready in the morning, I would be putting on about 3 layers of gloves and hand warmers. And if you had to remove any of these items of clothing to fix an instrument outside, you were at quite a high risk. So you had to keep every part of your body covered. I remember one day that I had a little gap between my hat and my buff, and I actually got a bit of frost nip on my ear. So it was quite a tough working environment. I am also often asked why I ended up here in this environment. As you can tell from my accent, I'm from England, and I've actually spent a lot of time in rain. So to actually move to snow is quite a nice thing for me. It's quite funny because when I looked back at old family photos, I found this of my sister. She's going to hate me for showing you all this, but we actually thought she was going to be the one to go into this field of research. So here I am in this on this expedition. But in some history, I applied for an internship at the Snow and Avalanche Research Centre 6 years ago. I ended up in the snow physics team. At that point, I had no idea that snow physics was a thing. So this was absolutely mind-blowing for me. And I was introduced to this concept that snow is constantly changing, and it's really this medium that's telling a story about weather conditions and the weather conditions that it's undergoing. So then I did this internship and then continued to do a master's in polar and alpine research, and then have now returned to the Snow and Avalanche Research in Switzerland for my PhD. And this is my first year as a PhD student, which I was able to join the MOSAiC expedition. So I've mentioned the MOSAiC expedition a few times now. This expedition was really a unique, one-of-a-kind experience, and we were basically lived on a boat which was frozen into sea ice. And sea ice in the Arctic is constantly drifting and moving. So the boat was frozen in and drifted with the ice, and we were able to work on and off the boat and return to the same locations on the ice. So we're really able to gain an understanding of what the conditions were like. It's quite an unusual thing to be in this region at this time of year. So this is the route that it was expected to take. So in September 2019, the boat was frozen into the sea ice and allowed to drift across the North Pole and to finish in October 2020. So one whole year working in this field. And the expedition consisted of about 600 scientists in total. There was some rotations of scientists, so other icebreakers would come and join this boat, transfer people, transfer goods, and then provide a whole new team to do this research. So the operations that were organised and the logistic challenges were absolutely incredible to be able to do something like this. I specifically travelled up in the beginning of February, and I was on the boat from March until August. So I returned in September time. So it was around 8 months in total. which is quite a long time to be in such an unusual environment. So I can tell you a bit about what life was like during these 8 months. It's quite hard to express this, but when you're living on this platform, this boat, is actually quite comfortable. So we have this stability, this home almost, which is really squeezed into the ice. We have one important thing is that we have to have a regular daily routine. So we spend around 7 hours on the ice, and it's very structured with meal times. And one reason this is important is because obviously we had 24 hours daylight, so it's very easy to become a little bit dislocated from the time and the location. It's quite an unusual feeling. But you really get used to this environment, and I can explain it like you walk off the ship and it's like your doorstep. So as you would imagine a tree at home, we really understand blocks of ice like this, and you can start to see how these are changing. And after spending 8 months in this time, it's quite an interesting thing to be able to see the landscape changing and notice the really small details. And you wouldn't have been able to do this otherwise. So that was really, really interesting. One important thing is the navigation around this area. So there's different areas of the ice around the ship, which are designated areas for specific pieces of science. So you really need to understand the environment and be able to navigate easily around here. And as you can see in this photo, it sometimes gets quite difficult because the landscape that you get to know so well, it's moving. So it often, the ice undergoes, the ocean currents causes stresses on the ice, and these cracks appear. So mornings you can wake up and there's a new crack, and one site that you're really familiar with has completely shifted to another area around the ship. So the right becomes your left and your left becomes your right, and it's quite a unique thing to experience. Such a familiar place go so unfamiliar. Another thing would be that you have to be aware of your surroundings because there's polar bears. We're in polar bear regions, so we had a logistics team who were polar bear guarding for us. And this just emphasizes how remote we were. So very close to the North Pole, all the 24-hour daylight. It's so remote that you need to have so much preparation for an expedition like this. You can't forget anything. You can't one day realize that you need an extra pencil, but you've not packed one. So the planning to get to this level was years and years of work by many people involved. And there was also this responsibility that you have to troubleshoot equipment. So if anything breaks, it's the responsibility of people on board. So it's quite for me, it was an incredible opportunity to be able to be here with this, such a variety of people working on different things. So I can then start to talk about exactly what I was researching. So coming from the Snow and Avalanche Research Centre, obviously my focus is on the snow. I'm in the ice team, so it's a part of a larger team, but I'm trying to understand the spatial and temporal changes of the snowpack. So we get ice, basically a collection of ice, which is different ages. And so you have ice, which is the first 1-year-old ice, which hasn't undergone a melt season. And you also get ice which is more than 1 year old, which has undergone melt season, and then it turns into this older ice type. And I'll talk more about this later, but that's quite an important concept to understand. We also get different topographies. So in this photo, you can see an example of ridges. This is when ice is pushed together and creates these mini mountains. And also on the image before, you can see these cracks, and this is also one area of study that we're interested in. It's a very windy environment, so all of these different different ice ages, different topography, really creates this uneven distribution of snow. You can see here that we have quite a lot of accumulation on ridges. So one thing is to understand just how the snow is distributed. And we would do this by having designated snow areas. So there were specific areas which would be kept untouched, and we would go in and research the snow properties in this season. So that was a really unique opportunity to be able to return to the same site and see how it's changing week on week. So why is snow important? I can take you through the bigger picture. So there was people on this expedition who were really researching a large variety of things, but specifically for snow, it links quite a lot of these different concepts. So, for example, as heat is transferred from the ocean to the atmosphere, snow is the insulator of sea ice. So snow is really protecting it from any warm air fluxes, warm air intrusions coming from the atmosphere. It's also important to understand the snow for remote sensing applications. So, for example, when we're trying to measure ice thickness and ice age from satellites, the heterogeneity of the snow actually causes quite some difficulties when doing this. We need to understand how the mass is distributed, and snow is the thing that is being blown by all this wind. So we need to understand where snow accumulates, to understand where mass is distributed in the Arctic. And also in summer, I said that we had 24 hours of daylight, but really the understanding light transmission is important for optics and algae growth in summer. So here's just a show of how many people would be working on the ice at the same time. It was really a huge collaboration of many different people working towards these goals. And this is just an example of me sitting with a colleague, Stephanie Arndt, in a snow pit in quite windy conditions on this day. So we would really sit in the snow and look at dig a wall of snow, which would look like this. And we would be able to tell a story from the different layers that we're seeing. We'd be able to see that it has temperature gradients, and we'd be able to see that there's been fresh snowfall on top. But we'd have about 2 hours to look at all of these different parameters that I've just listed around the circle. And the instruments that we use would be a huge variety. So we take this whole table of instruments onto the ice with us to try and understand the snow conditions. But one instrument that we have actually on board is a microcomputer tomograph. And with this, we're really able to see the microstructure of the snow. And it's an instrument like you would get in hospitals. It's exactly the same, so uses X-rays to understand the micro. And from this, we're able to understand the different layers in the snow at really, really high resolution. So it's a really valuable tool to be able to have on the boat. And to be able to install this on the boat was a really unique opportunity. So from a profile like this, we'd be able to see that, for example, we've had some fresh snowfall on top. A 3D reconstruction would look something like this, of really, really fresh snow. We'd also get some wind-packed layers, and we'd get some, when the snow is heavy, we'd get some water infiltrating into the side through, if the water level goes over the ice surface. We would also get really extreme temperature gradients, so we get a lot of changes of the snow structure inside the snowpack. So just understanding the conditions in the atmosphere helps us understand exactly how these grains are positioned in the snow. And we'd get some really incredible structures like this. With these transfers of snow grains, of ice crystals, we would actually start to see snow or particles from the ice surface move up into the snow. And I've mentioned different ice ages before, and basically I've just mentioned that we have different ice ages. So we have first-year ice and second-year ice. And at the moment, we're starting to see a larger transition into first-year ice, an Arctic with more first-year ice. So this is ice which isn't lasting a season. And with this, it actually means that the ice is saltier. So it doesn't have the summer to wash out the salt from the ocean. So we have salty ice, and what we actually found, which is one really unique initial finding from the expedition, is that we actually started to get salt being brought up into the snow. So this image on the right, the red parts are actually, we're able to really locate the salt which is being brought up into the snow. And this is really interesting for nutrients and exactly how the reflections that we get from remote sensing signals could have quite a big influence on having this third component, this salt component. So what I'm trying to say is that we're seeing this new Arctic, so this younger ice, Arctic with younger ice, and what we were trying to understand is such small details of how this is influencing the larger picture. So with that, I think I'm going to finish my presentation. I think I've overrun a little bit, but I'd just like to say thank you for having me. And yes, I hope it was interesting.
Thank you very much, Emi, for your talk and for sharing with us your experience. Now it's time to Julia to talk about the use of drone in the study of climate change. She loved the snow working outdoor, and a very funny story is that she told me that she realized that working in Davos was the right place for her when the first time she was there. She has saw the fact that the people that work there didn't have a car, but maybe more ski parked outside the office. Julia told me also that to fly a drone, we do not need just a pilot, but also a co-pilot. So thank you again for being there, and it's your moment.
Now you can hear me, I guess. Hello, everyone online. Thanks, Maria Sole, for this nice introduction, as well as to the entire NanoTalks team for inviting me. It's a rare and nice opportunity to bring our research to a wider audience. And I'm emphasizing our research here because I'm lucky to be part of a very collaborative team, which includes Johanna Malle and Claire Webster. And in the process of discussing tonight's talk with the Nano teams, we ended up on topics that are actually largely their expertise. So I'm very happy to contribute to this work, but the merit of what I'll show is actually mostly Johanna's. And so just as a background, just as background, we are part of the snow hydrology group at SLF, and the group is mainly interested in snow as a part of the hydrological cycle. So we study the processes that control how the snow accumulates and how it melts. And we're interested in how these processes vary in space and time, especially also in forests, because that's where they are most complicated. And our work then directly feeds into snow models that are used by our group to do forecasts of the snow distribution and the snow melt over entire Switzerland and throughout the whole winter. And this is a service that we provide to BAFU and so indirectly to the public. But today, I'd like to look at our research from a somewhat different angle. So I'd like to give you sort of a glimpse into a day in the life of a forest snow scientist. How do we work? What do we look at? And this is now not in a hydrological context, but within the context of this big topic of climate change. And so we'll start by looking at why we care about snow and forests in the context of climate change, or better, why we need to look at snow and forests carefully if we want to understand and predict how the climate is changing. And then I want to try and explain why this is a complex problem and why the drones can really help us in tackling this problem. And finally, I'll show you a specific example from our science, from how we use drones to study forest snow. This is from Johanna's PhD project. So let's start with really my favorite bit, snow. Now, snow is really a most fascinating material. It's extremely complex, and everyone who does backcountry skiing knows that it can change really, really quickly. And as I summarize it here, snow is a hot material that keeps our Earth cool. So that may sound a bit weird, but it's actually really what it is. Snow is bright white, and that means that it reflects most of the incoming solar radiation back to the atmosphere. This can be up to 98%. And this obviously drastically limits how much energy can be absorbed by the Earth and contributes to warming. But at the same time, snow is really hot. So from a physical point of view, a hot material is a material that is close to its melting point. And with snow, that's the case very often. And unfortunately, this aspect also means that snow is very climate sensitive. So a small increase in temperature can mean a transition from snow to rain in many places and very often. Then forests are also very important for our climate. One of the main reasons for that is that they act as massive carbon sinks. And that's not just because the trees do photosynthesis, but also because forests soils store huge amounts of carbon from decomposed material that has accumulated there over the millennia. And at high latitudes, this carbon is locked into so-called permafrost, so permanently frozen soil. And now the forests are experiencing pretty drastic and rapid changes. You will have heard of that wildfires are becoming more frequent. Another example is widespread tree mortality because of insect infestations. And the combination of forest loss and also thawing permafrost is both reducing the capacity of the forest to take up carbon and also causing massive carbon release to the atmosphere in form of methane. And so now these are two important players. And in our research, we're interested in a phenomenon that involves them both. And this is the so-called snow albedo feedback over forests. I should say here that albedo is the fraction of the radiation or the incoming radiation to a surface that is reflected back to the atmosphere. And so generally, this snow albedo feedback describes a positive feedback loop by which you have an increase, an initial climate forcing, which in our case is man-made, and this causes an initial temperature increase. And this increase in temperature will cause snow extents to decline, so less snow, we will have a darker surface. A darker surface can absorb more radiation, and so this will cause more temperature increase. And this positive feedback loop is now leading to something that we call Arctic amplification. So it's a phenomenon that we are observing now. The Arctic regions are warming at a much, much higher rate than the global average. And now the boreal forest is part of these high latitudes, and it actually covers a large surface area in these high latitudes, and there the trees mask the snow surface. So this complicates this albedo feedback, and it has been shown that this is a large uncertainty of our climate models. And so this uncertainty, of course, arises because on the same surface, we combine highly reflective snow and very absorptive trees. And as you can see here, this variability is really the challenge. So these pictures are showing the main scene on 3 different days. You see that we have snow in the trees that has specific properties. We have sunlit snow, we have shaded snow, we have snow-free trees that absorb much more radiation. Then we also have snowpack evolution. So at some point we will have partial snow cover. And it's really not a surprise that models struggle to capture the albedo of such a scene, because so these climate models are really complex and they need to somehow simplify the processes that are going on. And so models assume that the forest is just a homogeneous layer, and this obviously does not correspond to a real forest structure. And now the issue is that it's really hard to quantify how much this simplification will affect the accuracy of the model, because we cannot really observe the important processes at the scales at which we need to model them. And now, again, using our example of surface albedo, we can measure it by installing a tower with sensors that look down at our forests, but then we will just see one point in space. Or we can use satellite data, which covers a very, very large area, but then it's really difficult to disentangle what's going on. And so our observational basis to tackle this albedo over forests problem is not really good. And now that's where the drones come in, because drones are gaining huge popularity in the geosciences because they offer us new perspectives and they offer us a lot of flexibility. So we can acquire data when and where we want, pretty much. And they allow us to see a lot of detail because we can fly close to the surface, but at the same time, they allow us to cover much, much larger areas. So to refer back to the example I just mentioned, they perfectly bridge the gap between the sensor on the tower and the satellite. And here I'm just showing 2 examples of drones to give you a bit an idea that the drones are not just drones. So the one that you see on the left is a commercial imaging drone, and that's quite easy to operate. It's quite cheap and it has a long flight time. While on the right, you see a multicopter. It's a very heavy drone. It carries a very expensive instrument. It's, the drone itself is much more expensive, and to operate such an instrument, you need a lot of practice and not a lot of experience. And with this, I also want to say that while drones bring a lot of new opportunities, they also bring a lot of new challenges. And so, especially for us working in cold environments, we are pretty much always operating at the range limit of the specifications. So we work at high latitudes where the GPS signal is more difficult to get. We work in the cold where the battery life is reduced. So it's not straightforward. And also, very often we want the drones to do something that they're not made to do. So the off-the-shelf solution doesn't really work. And suddenly a natural scientist needs to become a bit of an engineer as well. And finally, I should also mention that the popularity of recreational drones is becoming a bit of a problem. So now if you're in the mountains hiking, you'll very often see people just operating their private little imaging drones to take cool videos or pictures. And this increase in use of drones is really requiring new regulations. And that's also what's going to happen in Switzerland this year. So Switzerland will be adopting a new EU regulation that requires drone pilots to be registered and also to take a test. So now we're set up to look at a bit of science and how we have applied this new opportunity that drones are bringing to our research. So to illustrate the problem, here we have our complex forest structure, and we want to understand the land surface albedo, which is given as the fraction of outgoing shortwave radiation divided by the fraction of incoming shortwave radiation. And so our idea was to use a drone to perform measurements that would allow us to disentangle the different factors that control land surface albedo. And then like that, we would have a data set that would allow us to check if the model capture these effects. And so Claire and Johanna designed this albedo drone. So that's a commercial octocopter. And you see that they equipped it with 2 shortwave radiation sensor, one looking up and one looking down, and also with a camera with a fisheye lens. On the right, you see how the drone looks when it's in the air. And now the measurement principle of this instrument is that, so we would fly it over forests with varying forest density, and it would always hover at specific waypoints, and one waypoint is a measurement. And one measurement includes an albedo measurement, which is obtained by just relating the measurements from the 2 shortwave radiation sensors. And it would also include a hemispherical image. This image captures exactly the same perspective as the sensor, and it allows us to characterize the ground conditions co-located to this albedo measurement. And now, because this drone is such a flexible tool, we flew it on many days in different places in Switzerland, in Finland, with different meteorological conditions. And really, this allowed us to create a data set where we could disentangle, or we could look at individual effects of the ground conditions on the albedo. And as next, I'm just going to show you a few examples of what we got. So in this plot here, you see the measured land surface albedo on the y-axis, and on the x-axis, we have the fraction of visible snow that we could obtain from these images. And now the points include measurements along the same transects, but on 4 different days, as marked by the symbols and the colors. And on the images on the right, you see the example of one waypoint and how the snow cover changed over these 4 measurement days. And now this helps us interpreting the plot. So we have a very clear increase in land surface albedo the more snow we see. And we will have also more variability in albedo across our site on days with full snow cover, while if we only have very little snow, as you see with the green points, the albedo is very limited in the first place. So that's the example of how visible snow impacts land surface albedo. But then on top of that, so we have again a similar plot, land surface albedo plotted against visible snow fraction. And now the colors denote whether we have snow in the trees or not. And so the systematic increase of land surface albedo in the presence of interception shows us how this is an effect that we have on top of the visible snow on the ground. So we have systematically higher land surface albedo when there is snow in the trees. This is just a qualitative assessment because tracking snow in the trees with image analysis is really difficult. And now finally, here we have two plots with data collected just on clear sky days on very different sites. So we visited spruce sites, pine sites, needle leaf trees and deciduous trees. The plots are divided with needle leaf trees on the left and deciduous trees on the right. And now we have again land surface albedo on the y-axis, but now the x-axis is showing the fraction not of visible snow, but of visible sunlit snow. And this is now the nicest linear relationship that we saw so far. And this shows how really the sunlit snow exerts a primary control on land surface albedo. And this is quite an interesting finding because the shadows move throughout the course of the day. So what we're seeing here implies that the albedo at the same location will change throughout the course of a day. And now these are just examples that I showed to show you how we singled out individual factors. And this is really a quite unique data set that for the first time allowed us to check if the models are actually capable of replicating that. And so that's what I would like to link back to now, because we used this data set to actually check a climate model. So I'll just show you an example because this is work that has started now and will continue for a long time probably, because there's a lot to do. So what we're seeing here is, again, land surface albedo on the y-axis, and this is now throughout the course of the day. So the individual colors of the points are different points. We have the green ones that are in very dense forest and the brown ones in quite sparse forest. And here we clearly see the daily cycle of albedo, so the importance of the shadows, which is shown by the variation with zenith angle, which is actually just the variation throughout the course of a day. And so we have quite strong variations, especially at the sparse forest sites. And now we can test the model against this data. And we do that by running a model at each of the waypoints shown on this plot so that we can directly compare the model results to the measurements. And this is what we got. So two things are striking. First of all, we do not see daily cycles at all. So very obviously the model cannot capture this impact of the shading on the land surface albedo. And then I'd like to point out that the y-axis of the two plots are not the same. And so actually at the sparse locations, the model is massively overestimating the land surface albedo. And so there is a very clear positive bias for a certain type of forest. And now these results allow us for the first time to track down the reason for these big uncertainties that we find in climate models in replicating this process. So to wrap up, I hope that this talk has taught you something about snow albedo feedback over the boreal forest and why it's a difficult process to understand and to quantify, and climate models are currently struggling with it. I hope you realize that drones are great, but they're also hard work. So the data doesn't come for free. Off-the-shelf solutions do not really work, and we need to be creative with our systems to get something out of it. And yeah, then I hope you realize that so by creating such a new system, we were able to gain quite an innovative data set that really has the potential to advance our understanding of current model performance and hopefully also help us improve it. Yeah, that's as much as I wanted to show, and now I'm open for questions. And again, thank you a lot for having me.
All right, thank you, Julia, for those fascinating insights in your research. And I suggest that we now start with the Q&A session. And I have a first question to Amy. We were wondering, is there anything that you forgot to bring that you only realized when it was too late, when you were there?
Good question. So one thing is I was expecting to only be there for 3 months, and it turned into 7 months. So looking back, if I'd have known it had been such a long time, I'd I would have taken a lot more tea. Tea and socks. The socks got quite holy towards the end of the 7 months. So apart from that, all the scientific equipment was really well organized. I couldn't, yeah, it all worked out really well. So it was just some personal items. So spending that long on a ship would have, yeah.
And Julia, I would like to ask you the first question. And when we talk about drone, often some ethical questions arise. So I would like to ask you if you think that the use of drone in science is just positive or can have also a negative side.
So taking the perspective of a natural scientist, I see the new opportunities that drones are creating, and it's amazing. So it's quite fascinating just by looking at the number of publications that use drones. They have skyrocketed. They have really allowed us new insights. So from the perspective of a natural scientist, they are definitely positive. I think, however, that it's really, really good that they're being the use is being regulated now, and it will be easier to track who is using a drone and who is piloting a drone, and to make sure that these people have some background, or just at least some basic background knowledge, because I think, yeah, no matter if it's scientific or recreational, it's becoming too much. So it's too easy to pilot a drone in Switzerland today. So I'm very supportive of a bit of regulations, even if it does cause some additional effort to us, but I think it's justified.
Okay, and they ask you also if there is like danger for animal, for example, or accident that can happen with drones. If you,
I mean, there have been drone crashes. It does happen. The use of drone is quite restricted over areas where there are large number of people. Since I've mostly been a co-pilot, I don't have the details of how many people in what range, but you are only allowed to fly over certain areas and at certain heights. And for animals, so we are not allowed to fly over wildlife protection zones, for instance. And especially now in winter, there is this Wildruhezonen, and you're not allowed to fly there. So there are limitations, and yeah.
So another question for you, Amy. So you collected a lot of data during your time there. So what are you doing now with your data?
So yes, I mean, there's really a lot of data that we've collected, and it's when you're in the field and you're collecting it every day for a year, it's quite easy not to stay on top of the organization of this. So luckily, there was a lot of time spent into the organization of the data, but at the moment, it's mainly tidying up what we've been collecting in the field. Then we will start with the analysis and yeah, start writing some publications of what we've found. I mean, the expedition ended a few months ago, and there's already been some publications. So people are really, it's really a hot topic, and there was a lot of findings that we're hoping to start publishing now.
So have you so far found anything that you found surprising or that you didn't expect?
So I mentioned briefly the salt in the snow. So this was really the first time that we were able to see the location of this, and understanding that on a larger scale is going to be extremely interesting. We also, with my specific work, there was it's quite an interesting feature in the summer that when all the snow melts and the surface of the ice appears, we actually get this really porous ice surface. And to see a whole year cycle of snow cover and then this porous ice surface and then snowfall again, it was really interesting to see how this all came together. So we just wouldn't have been able to see this full cycle if we hadn't been there for a year, and then we can start to understand the implications for energy balances and heat transfers in the Arctic. So that was really interesting.
Julia, you talk about the feedback, and in science we can have negative and positive feedback. So we will want people ask if we have also, if when we study snow we can have both, so like negative and positive, or just one of the two we can use to study better the snow.
So snow cover extents are declining pretty much everywhere. So the snow albedo feedback is negative a bit by definition. But with boreal forests, it's quite interesting. There you can have a positive feedback because so snow is disappearing earlier. The growing season starts earlier and the trees starts to photosynthesize earlier. And so you start the carbon uptake earlier. And this is a negative climate feedback because you take carbon away from the atmosphere. Again, it's not as simple as that because you can have an earlier growing season, but then also more plant stress at the end of the season. So the net effect of these feedbacks is really, really difficult to quantify. And I find it quite fascinating because to really get to the bottom of this, you need to do very interdisciplinary science. And yeah, that's the part that I think is interesting.
So, Aimee, we had a question that was about the climate change. So, how does the younger ice affect the climate change in a big picture?
So it has quite a variety of effects, but one of them is that when you actually get younger ice, it's often thinner. So we actually start to see ice drifting a lot quicker and becoming a lot more unstable. So I mentioned these ridges forming. So we expect to see faster drifts and ice becoming more unstable. So that's one direction, and the other direction is the actual salinity in the ice. So I explained that the multi-year ice goes through a melt season and it is a lot less saline compared to first-year ice, which is really the ocean freezing and containing all of this salt. So this has quite a big influence when it starts to melt. You actually start to see different stratigraphies in the ocean depending on ice type that's melting, and also the different microstructure on the surface of the different snow microstructure on the surface of different ice types. So there's a few different approaches with this different ice ages. So it's quite it's a good question.
And Julia, they ask you, I know that you told us that you have been just co-pilot and never pilot one of that, but they ask us how is like the difference between pilot one normal drone and one of that one, because you explain us that it's more complex. So what is the feeling, if you can say like that?
So one of the straightforward answers to this is that it's just a different thing if you have a 15 kilogram aircraft in the air or if you have a 200-gram aircraft in the air. It's just, yeah, I think it's more, you know, they're louder. They make, you have a larger air, yeah, just this pressure wave when they get up. So it's, and also the larger ones are more unstable in the case of wind. So if you're more nervous about the wind conditions, and this when flying them over forests, that's quite an important point because often the wind conditions, they change just above the forests. So you start and it seems okay, and then suddenly it can change a lot, and that's something that you feel more when if the drone has more inertia, and so also the pilot. So the piloting, once the drone is in the air, you send it on an automatic program. So while it's doing its thing, you don't have to interact much. But then when you take it back down, also the landing is more difficult. If it's a heavier drone, you need to be really exact about the landing.
But you have to do like a school to
yeah,
learn, or It's just like you have to practice, and after.
No, for these big ones, you need to be in, or your employer will need you to be insured, and so you take a course to get that insurance. While for these small ones, I think you can just buy them and pretty much learn yourself. And children can fly these drones. Like you see that often.
So Amy, you spent quite a long time on like a ship in sort of unique environment. So has this experience changed you as a person? And if so, how?
I think I would say yes, just because I like to be quite structured in my planning, and you have to have this before you go on one of these expeditions. You have to be quite prepared for your schedule and having everything in order and knowing what's involved. And when we had so much uncertainty because of COVID, so all of our plans completely changed. And I think this really change of plan, it just wasn't in my schedule. So it was learning to be adaptable, definitely, especially in such a location where, I mean, it's completely out of your control, and everyone around you is also in this situation. So that was definitely something that changed. I mean, it's just being able to adapt to situations like this, I think.
And I would like to ask you something to both, because you both work a lot of time outdoors and in Davos, or as you, Hemi, in the Arctic, we have like extreme temperature. But I think that when we have to stay all the day outdoors working, it's not easy in the snow. So I would like to ask you how you keep the focus on what you are doing, and not like thinking about, oh, it's so it's freaking in, it's cold and things like that.
Do you want me to go first? I can go first. For me, there's always such a structure to the day, and when you're working in the field, it's almost, you need to be so focused to get everything that you want to get done in these hours available to you, or in this half an hour available to you. So for me, it's the focus is really on productivity, and then obviously you need to make sure that you're comfortable working in these situations, and it's all about the equipment that you have to combat this. So for me, it was quite important in my work to not be uncomfortable. As soon as you get uncomfortable, you need to change the situation, either put more layers on or go inside, because it can start to get dangerous. So it's actually, you need to be productive, but also you need to be very aware of what conditions you're in.
I would sort of support what Amy's saying. I also must say that I have never worked in cold environments as Amy, so I think the worst that it got here was maybe -27, something like that. So for me, it's always been that during these fieldwork days, so I often had to coordinate people, students, interns, and to just make sure that everything was working, that the work makes me forget about the cold, even if I'm a person that tends to freeze a lot. But yeah, the equipment is everything, and sometimes you just need to take a break and get a warm cup of tea. But I really like working in the snow. And maybe I've also always been lucky that my fieldwork is not, sitting in a snow pit and just looking at very detailed stuff, but I always had to move around a little bit. That helps.
Okay, so Amy, maybe one last question for you. So you spend a lot of time in an extraordinary place that you really could not leave if you wanted. So did it have like some psychological aspects of you? And did you look forward to sort of leave that place at some point?
Yes, I think it's a good question because it is such an unusual environment, and it's so, the environment is unusual, but also the social side is really unusual. I mean, you're surrounded by 100 people all living on this small boat, but you have to get along with everyone, and there's not one single moment that you're alone. Because even when you're working on the ice, you have polar bear guards and people working together, and the cabins are shared, and then there's evening activities. So there's always people being together and supporting each other in these situations. And absolutely, it was difficult to be faced with so much uncertainty. And for me, I was quite lucky in a sense that I had a very supportive supervisor and family at home that it didn't matter that I was away for such a long time. But obviously with people with families who were going through this pandemic, it was a completely different story. So you had to be quite aware of people going through different situations and finding it difficult. And I really loved the work and I loved the people there. So it was really easy for me to continue with the work. So just extremely grateful.
And Julia, also the last question for you. Do you think that communication related to the climate change and the scientific work, also if you want to answer, it's good, or how we can improve, like to say to the society what is really important?
I might start. I'm not sure if we are the right people to answer this question, because we are on the science side. So I see a lot of what's going on regarding science communication, and I'm like, okay, we do a lot. People just have to listen to what is being done. But I don't know, how this sort of outreach and advertisement is perceived by the people. So it would be interesting to ask this question to someone who does not work on climate change.
Yeah, but if you have the chance to say something to the people that maybe are watching you tonight, that maybe they didn't know yet about climate change, because we don't speak a lot about this field. Like, we speak a lot about climate change, but not like, for example, what you presented tonight. There is something that you think it's really important that people know, but we don't speak a lot about that. So you have the chance tonight to say to the people that are watching you.
Amy first. I'll think about it.
I think for me, it's just to be, if you find something interesting, and if you are, if you find something about this topic interesting and you want to find out more information, or you want to go into this sort of research, it's really possible. And if you want to make a difference and try and understand a process better, or trying to speak to the general public, the platforms are there, and it's just making use of it. And I think, if you're not happy with a certain process, is to really find similar people who are also uncertain, and to just get more information about this. I don't know if that's really answering the topic, but
yeah, I thought of something else. So I agree to what Amy's saying, very important point. And what's been really important for me in getting interested in this topic is really like, have your eyes open when you're outside, because like you see a lot of these impacts, or of the impacts that humans are having on the environment. You see them. And so I think if people just, were a bit more aware when they go out and enjoy nature, because a lot of people like to do that, I think that would yeah, that would help change the perspective of. So open your eyes.
Okay, thank you very much both. So following this question, unfortunately, it's time to finish our Q&A. I would like to personally thank Julia and Emi for being with us this evening, and also you for following us live. I would also like to thank you, Luca and Joel, for helping us organize this evening. And the NanoTalk will, of course, be back next month, the 25th of February. And I really hope you will be with us soon and you have enjoyed this evening. So thank you very much. Thank you, Yasmin, for helping me tonight. We have a great work together, and have a nice evening.
Thank you.
Thank you, everyone.
All of this.
Thanks.